We cover benchmarking. We measured performance with some little tiny examples, but we're going to show you the real world case when we're executing with large programs and how we measure the different execution components. We're going to look at different types of workloads. And we're going to go from single core to multi-core. So everything we've done so far has been single core processor. Today, most processors you buy are multi-core, so we're going to explain the transition to that. The exception is embedded systems. Embedded systems have very specific purpose. Maybe they're very limited computational need, or Internet of Things is still single core. But we'll talk about a very profound way of measuring performance for multi-core called Amdahl's law. So let's start with benchmarking. The easiest way to see an example here is to look at some of these websites and benchmarks, like standards as many benchmarks to choose from. Benchmarks consist of programs that are used to measure execution time, and they're organized into a collection called a suite. So benchmark suite is a collection of programs. And if you go here, we can click on some of these. You can see, let's say, low to mid-range, different range systems. You're looking for a server, so forth. These systems were all measured. These are kind of very close together. Let's look at a different class.
I'll do the high end.
You want to do high end? All right, go for it. Yeah. So here's some high-end servers. You get this one number, which is part of our discussion today. How do you end up with one number from all these different program execution times? And you can see here the processor, the clock rate, and the cost. So this is a quick way I like this website actually, because it's pretty much constantly updated, and it's a quick way to compare costs versus performance. You can click here and see a bunch of ads and you want to buy these things, and also the breakdown, okay, of how the different machines performed against this benchmark. So benchmarks, we're going to see more examples, are a collection of programs to measure performance and aggregating this into one number. And you're going to say, well, still, how do you keep track of all these things? I'm just passing this along because I thought this is one of my favorite websites. I like at non-tech, and you can just see here. They're not too technical, but they're technical enough. Some are too marketing, and some are these things could be like religion too. It's like some people, no matter what it is, they think AMD is the best, and maybe they're right, but they think Intel's the best, or I think the articles here versus like maybe Tom's Hardware and some other ones, these guys are pretty balanced, I think. And they're a little bit more technical, scientific. So when I have time, I go, maybe not every week, but every other week or so, and scroll through and see what's new on the web page. And click. This was benchmarking performance to do this graphics task, and they looked at some basically things we're talking about in the class. I just passed this link along, okay? So I like it non-tech. Let's look at benchmarking. As I mentioned, benchmarking is a set of programs to measure execution time for a particular class of applications. For example, scientific, arithmetic computation is one class, graphics another class, text processing another class. Our job as a performance engineer is to look and see what is the user's mix of these different benchmarks in their real intended application. So if you have a customer that has a specific need, the better you understand that need, the better you can deliver a system that matches that within cost constraints. The easiest way to see this benchmarking in action is to look at this video. Here is, they've aggregated this using harmonic mean. We're going to show harmonic mean, geometric mean. This is a PC-based one, but you can run on a server also. Actually, I think there's no sound, just music. Yeah. This is actually a pretty nice program. You can go and graphically select what you want to benchmark. And what it does, it goes into the system and it'll figure out all the different configuration information, capacities, access times, gigahertz, based on the model of the chip. Then you can go and start running some of the different benchmarks.
So you can build a board and this does that?
Well, this is actually the real board that you have in front of you, but you can say, what do you want to benchmark right now? So here's the system performance data for this computer, and you can benchmark this versus other ones that you're comparing. That data comes from the web, and you can measure yours against theirs. It's just showing an example of measuring with benchmark. So they're going to run a bunch of tests. They're going to test memory intensive. They're going to test integer intensive, scientific workloads. Each one of these is a program. They're going to run the program, measure how long it takes to run. And you can see here, oops, frames per second throughput, right? Operations per second, that's MOPS, right? Millions of matrices per second. These are throughput-oriented metrics. So he's going to now select a benchmark. So integer, it takes some time to run all these. He's just fast forwarding here. Graphics benchmarks. I/O benchmark. You come up with one number. This is a CPU mark. It's aggregating the entire performance of that machine relative to some standard, which we're going to talk about. So something called pass mark is what this program uses. Let's stop this for a second. And what we did is we ran a bunch of benchmarks. Some are CPU intensive, some graphics, I/O, memory intensive. Remember our different instruction classes, right? Each one of those took a certain amount of time to run, and the way that these were aggregated was adding the reciprocals of the times together and taking the reciprocal of the whole thing is the pass mark rating. This is using a harmonic mean to aggregate these. Whenever we do statistics, we have a lot of data, but we want to be able to compare things, right? So, for example, house prices, right? So we have median house price, mean house price, different ways of aggregating this information. There's standard deviation and all these things. So sometimes one metric is more important than another. We always tend to like things like median house price when they have outliers, right? So there's one value that's super large or some that can throw off the average. You know, there's so many $1 million homes down in
California.
Yeah, California, but also down here in Orlando, right? What's the lakes, right? Say again?
Winter Park?
That's it. Oh, Winter Park, yeah. Winter Park, right? Winter Park, Winter Park, all the rich guys. And no, I'm thinking, what's the?
Like Nona?
No, yeah, they like Nona too, but Windermere, that's it. Windermere, right? Whenever you have a lot of silent E's, that's my heuristic algorithm, right? If you have a lot of silent E's in the name of the word, that means the price is it's going up. Each one of those, you can't pronounce it, but you have to pay for it, right? When you see like fancy English words and the shops of Winter Park with the E on the end, it's price. But here, this is aggregating, so this number is not really representative as a whole, but it's kind of like an aggregate behavior. Whenever we aggregate, we lose information, but we have a way to comparing now this system versus another system. Of course, the system takes into account many different aspects: the performance of the CPU, the clock rate, the CPI, the memory interaction, the front side bus, the back side bus. Well, how do we aggregate all these? This is one number representing all that information. So we're going to see you need to know what your benchmark is that the customer cares about. And then you can drill down into the details and find out what the different components were that, well, this is actually telling you here, these numbers. We pretty much saw everything we need to see. Okay, so this is one sample program for your Measuring performance of a PC-based system or server. What's one issue with that program? Oops. What's one issue with that program? Pass mark. Let's turn it off first. The question is, who chose those workloads, right? Maybe, suppose it was Intel. They may choose workloads that makes their processor look really good. Or NVIDIA, right? They may really weight the graphics. So there's this thing called SPEC, which is a consortium of companies. What's consortium? Industry consortium.
Organization?
Yeah, it's an organization. It's a collection of companies. It's like a nonprofit. Actually, this is a nonprofit called SPEC, System Performance Evaluation Corporation. And it has all the chip manufacturers and server manufacturers get together and they kind of vote on what they think is a good representative benchmark to measure processor performance across a number of different workloads. Actually, I've summarized them here. You can click on their website and get all the details. Too many details, actually. But here you can see there's a 12 integer benchmarks and things we kind of do every day. Compress files, FPGA, I love it. Placement and route, and ISE, right? You guys use ISE in the Basis 2 boards. Maybe you compile a C program, compress a file. Yeah. And then there's also some scientific applications. So this is what's inside the SPEC benchmark set. But the key thing is that multiple companies voted on that. It's not going to favor artificially one or another. That's another mini story, is that if you are a CPU designer, there's an old trick, and that's one of the reasons they came up with the SPEC, is that once you know the benchmark, a little secret is you make your cache big enough so that the benchmark fits totally in cache. As we're going to see, as we're going to see later in another module, is the cache is about 10 times faster than main memory. So if you make your cache just large enough so that the benchmark fits inside, your processor looks like so great against that benchmark. Now the data set gets a little bit larger than cache, and then your processor is doing terrible, actually, but nobody ever saw that because they look at the data sheet and this benchmark results, and yours was looking really great, right?
It's good for sales.
It's good for sales, marketing. So just keep that in mind. We have a saying that you may hear, make the benchmark fit in cache. So that's the trick. So we look here, SPEC. They have a website. You can go there. I'm not going to take too much time. It's a good thing to do out of class. You can browse this. It's the same. They'll have a bunch of results, for different. They have all different versions. Some are more math. Some are. We use CPU 2006. This is kind of the balanced one. I just showed you the chart. Right? But they have some are even going more math and going more this and going more that. And you can run it on your own machine the same way. They have different types of workloads here, and they discuss all these different aspects. A whole bunch of papers here, and this stuff is usually kept up to date. So SPEC is the non-biased version of benchmarking. So let's put this in practice and look at what some of these numbers mean, because some days we're going to get to this. The customer wants you to make a trade-off or is paying you to meet some performance objective. So the way the SPEC ratios work is they report the results relative to some reference. There's an equation. The SPEC ratio for machine A is the time on the reference machine divided by the time on computer A. So time on a reference machine, they pick an old machine, maybe 2006 for this 2006 benchmark. But we're going to see, because we use geometric mean, it doesn't affect the answer. It's just giving us some benchmark. It's giving us some benchmark, and then we can get this ratio of all machines relative to that. So this ratio is called SPEC ratio, you'll see. If we take the reference execution time relative to the machine A and then the reference relative to machine B, gives us the performance of A relative to B. Why? Because times and rates are reciprocals. Performance, right? You want performance to go up, you mean you want the time to be less. You want to be a faster runner, high performance. You want your 5K running time to go down. Time and race are reciprocals. Performance and time are reciprocals. So we use geometric benchmarking to aggregate these individual scores. You saw that what do you have with the 1 over, they call harmonic. So here we're using geometric, and I'll show you why. This is not on the test, but it's just for people interested why geometric mean. Because if you have a geometric mean and another geometric mean, the ratios of the geometric means of those ratios are the ratio of the means. So what happens is if we have some reference machine and we're giving our ratio relative to that, the components of the ratio reflect into the ratio versus of the overall number. Harmonic mean and some other aggregation techniques don't have that property. So what does geometric mean? We take these spec ratios, we'll show you how to calculate an example, next slide. And we take the product of these. So geometric mean is defined as follows. This symbol is the same as summation, which is sigma. To do addition, but this is doing the product. So the product of of sample sub I from 1 to n, right, is defined to be sample sub 1 times sample sub 2 up to sample sub n, all multiplied together. And then to get the geometric mean, we take the nth root. This is helping us smooth out some outliers and some other behaviors, but has a nice property that this ratio of the means is the same as the mean of the ratios, is not disturbed by this process. So let's try an example. Here we have some measured data for a reference machine and 2 computer systems, and the scenario is you want to see which is better, system A or system B. Better, right? It's in context of the user, context of the customer, but here we're using some set of benchmarks and we're aggregating these and comparing them. So we have 3 workloads: CPU intensive, memory intensive, and graphics intensive. They can be anything. I'm just giving you 3. They're actually hypothetical, made up values here. So what does this mean? The reference machine took 20 seconds to run that workload, which is a CPU intensive. Your processor A, your computer system A took only 4 seconds, and another system took 5. So first we compute the spec ratio. What's spec ratio? You remember it's the reference divided by the time of reference divided by time of A. So was that 5, 6, 4, 3 divided 5, 6? And you say, what do those mean? That's a good question. That's a declarative statement. Basically, this means it's 5 times faster than the reference machine. What's a reference machine? Well, it's a SPARC workstation from 2006, but we don't worry about that. Maybe it's an Intel something or other. Someone picks a reference value, reference machine, and they're going to report these, and you can compute your score relative to that, and we're going to show you why. You do the same for machine B. Is there any units on this? No. This is time divided by time. This is a ratio. It's unitless. So what's the spec score? Spec score is defined to be the product of the ratios and then the nth root. So how many ratios do we have? 3. Take the cubed root, right? So 5 times 6 times 4, cubed root of that, 4.92. System B, sorry, the animation came out of order on this. 453, cubed root, 3.9. These are the spec scores for A, spec score for B. You can go to the spec website. You'll see spec scores for all different machines. Dell server model such and such with the so many gigahertz clock, this many gigs of memory. This was a spec score for that. We saw the 12 integer and the 16 or 17 floating point benchmarks. They ran them and they measured it and they reported it and they aggregated it into one number. This is for this machine. But you're going to say, how do these two machines compare? Well, this is 4.92, this is 3.9, so this is the ratio, see, ratio of spec scores. Can somebody give me a declarative statement when I see this? So why do I care about declarative statement? Well, hopefully You can plug and chug and put numbers in here and get this and then say, okay, well then what did you learn? So the number comes out 4.92. Somebody give me a declarative statement. What is that saying? 4.92. Anyone take a chance. 4.92 is a spec score for it. Ted.
A is about 5 times faster.
Yeah, exactly. A is roughly in aggregate, using this aggregation method of geometric mean. That's a lot of extra words, but I like Ted's statement. System A is about 5 times faster than the reference machine. What's the reference machine? You got to go look it up. It's in the spec there, but okay. What about the ratio of spec score is 1.26? It's 1.26 fold faster, which means what? System A is roughly 25% faster than System B using these workloads. Change of workloads, you're going to get different numbers, but here's workloads. Are these like the only workloads? No. Is this what your customer has? Not necessarily, but this is some set of workloads. Right? Any information is, better than no information, but you have to understand what it's measuring. You can go inside there. Does your customer do any word processing? There was there, right? Yeah. Okay. So these numbers have some physical significance. Again, this to me is a nice thing to walk away from and have some intuitive understanding of what these numbers are, right? What these mean. The ratios of performance. Let's try another example. There's a new computer system on the market. We need to determine performance, and someone asks you to use spec procedure just because it's less biased. So you go for it. So here's some measured data, and you have to figure out find the spec ratios for the individual programs listed below, then the overall spec score. So the ratio of execution times. Ratio is 2, which is faster? New computer, if the ratio is 2, is your new faster or reference?
Twice as fast.
Twice as fast. That's another way to help remember this is if you forget, if you want this number to be greater than 2, less time means faster, so it has to be in the denominator. Now I get to spec score, right? There's 4 different measurements. So it'll be the 4th root. Okay. And you're going to say, but Professor DeMary just said we can't use complicated calculators in the exam. What are we going to do? That's a good question. So here's a way of solving this using powers of 2. So I have to compute the 4th root. What's 2? 2 to the 1. Does anybody see powers of 2 here? Times 2 to the, yeah, times. So that's the 4th root of what? 2 to the, so what's the 4th root? 2 to the 8th raised to the 1/4. So when I multiply powers of 2, I add the exponents. If I take powers of 2 and root them or square them or exponentiate them, what do I do with the multiplier? Can you multiply 8 times 1/4? You definitely can do it, and you can do it in your head. It's 2. What's 2 squared? You got it. 4. So, if we give you more than 2 on the exam or the quiz, I'll make them powers of 2. And since you went to class today, you'll know how to solve these without any heartburn. So we always look for powers of 2. Powers of 2 make us look smart because powers of 2 are always coming up. All our data sheets, a lot of these measurements and stuff. And sometimes you say, well, it's not always going to come up power 2. Maybe not, but you can estimate pretty quick. And then, there's 5 companies on the Skype phone call, and you're looking pretty smart because you can estimate these pretty quick. Now, like, can you do multiplications? You can also do roots and squares by just multiplying exponents rather than adding them or subtracting them. Okay, so help me out with declarative statements. What is that as a declarative statement? Roughly 4-fold speed up versus the reference machine. That's what spec score means. Relative to the reference machine, in aggregate, it's about 4 times faster. Well, yeah, I mean, CPU was only twice as fast, but then go to something else. The graphics was 8 times as fast. So give me one number that's representing how much faster this whole computer is, and on average, or I don't like the word average because people think it's arithmetic mean, right? What's arithmetic mean? Exactly. 1 to n, and divide by n is arithmetic mean. Right, with different types of means, it's arithmetic mean. I didn't come up with these words, it's from math class. Arithmetic mean. Harmonic mean was taking all the reciprocals and then taking a reciprocal of that. And then geometric mean was this arithmetic mean. But I just say average, because if people think of this a lot of times is average, okay? Kind of implies arithmetic, but in aggregate, okay, is that?
What's the benefit of using one over the other?
If you use geometric, then we're keeping the ratios of these subparts. So in other words, it's helping us get rid of some outliers and skew, and also maintaining this ratio of means as the mean of the ratios, which it happens more than when we dig into the next level of this. I can show you some examples offline. I'm not holding you responsible for that. But it helps us smooth out some things and helps us to keep this ratio. So basically what I can do is I can take the ratio relative. So if I know my spec score is 4 and your spec score is 6, I can take the ratio of the spec scores and know my machine, well, your machine is 1.5 times faster. If you don't do geometric mean, the numbers lose their ratio relative to the reference. So what's another? Okay, so another way to say this, right? This is 4-fold, which means 4 times faster, right? What about that? Sometimes you're on a phone call and the customer wants, I've got this whatever Dell server, it's going pretty good, but it's like 5 years old, and I got a lot of new customers now, business is good. Here's 50,000 bid is out there if you want to bid this to reduce my execution time by 75% for customer queries or whatever it is, and that's really what they will pay you for. So what spec score minimum are you looking at? Suppose they had the reference machine. Are you looking for a spec score 75? Are you looking for a 75 over 100? Because 75 is a percent. Percent means per 100, right? That's what it means. True, but why is a spec score of 4 good? Because if it took, try some numbers. 4 means that the time of the reference divided by time new, by definition of spec score, right, is 4. So suppose it was 4, was the reference is how long it took. What's the customer want to get it down to? 1, because reducing by 75%, right? Here's a pie chart. It took 1, 1, 1, 1, and the total time is 4, right? There's a sum is 4. He wants that to go away, that to go away, that to go away, so it's reducing it by 75%. So the new time has to be 1. So 3 seconds has to go away. So how many times faster does it have to go? So if 3 seconds goes away, it used to take 4. And this is the old, right? T old, what's T new? To be 75% faster, T new has to be 1. So you got to practice these and know what these mean, because sometimes the customers say, I want to go 75%. I want to complete in 75% of the time that I have now. You need to know, like, go to the table, you don't look for a spec score 75, you look for a spec score 4. So now we have different benchmarking metrics, and then, so you're going to say, well, how does this relate to CPI and multi-cores and execution time? there's this so-called triad of performance showing CPI, instruction count, and cycle time, all influencing execution time, and they're all pointing at us in different dimensions, different ways. But someone may ask you, what's the best metric for a program like you only got space for one? If you talk about all the components of a CPU working together, we had I just erased it, processor and the memory and the data bus and the bus rate and the front side bus and megahertz and CPI, all these things happening together, they're all going to influence execution time. Remember, response time is what the user sees. Execution time is the CPU's component of that. Maybe we're not network people, we can't influence that, but if we're designing a processor, we can influence execution time. So execution time will intrinsically incorporate all those factors in how the user actually will see the result. So it turns out benchmarking, so somebody asks you, what is the true performance of a computer system? That's what we measure with the benchmark. When all these pieces work together, branch prediction, different types of multiple levels of cache, optimizing instructions, changing the order of instructions, compiler optimizations. Well, those are all things that help, but what's the final answer? The final answer is how long the program took to run. So you're going to say, okay, this is good. Everything we did so far was good for unicore, but all processors today that are not for an Internet of Things application, which is a whole big application area, which is embedded systems, actually, next class, have multiple cores. We have Amdahl's law. It's going to help us understand that, and this is a really cool insight. And let me show you this. And this is the thing, if you see the right conceptualization, it's amazingly simple, and it's amazingly powerful. If you just want to memorize it, then it becomes complicated. So let's understand the concept first. We speed up a computer component by a factor of n, which means suppose we make either processor or memory, one of the two, but not both, n times faster, then the overall execution time will speed up by a factor smaller than n. It totally makes sense. Improvement depends on what proportion of the time that the component is used. That's all that Amdahl's law says, but it provides us a nice way to calculate that in a very powerful, expressive formula. Our first insight into Amdahl's law is expressing the time new versus the reference machine. It's a proportion of the time that was not enhanced by this engineering improvement, which someone's hired you to do, plus the proportion that was enhanced divided by the speed up of enhancement alone, which we're calling n. Okay. So the easiest way is to see an example. Execution time of a program is comprised, in this abstraction, right, it's an abstraction, 3 components. Processor, 3 seconds, memory, 10, hard disk, 5. This is I/O, this is memory, and now we see the difference, right? We just had that question. If we're able to speed up memory access so that it's twice as fast, what's the impact to our best metric, which is how long the program takes to run? How do we solve this problem? Well, here we have some proportion that's not enhanced and some proportion that's enhanced. Before I show the answer, what proportion is being enhanced if we speed up the disk by 2? Factor of 2. I'm sorry, memory. I just said disk. We speed up the memory access. Memory access by a factor of 2. So memory is going to go from 10 to 5. We're going to change these other 2? In this enhancement, no. So the time not enhanced is 3 plus 5 is 8. The time enhanced was 10 divided by the speed up factor. How much are we speeding it up? 2. So we see that math right here, right? So 3 carries down with no change. 10 gets divided by 2. That's the speed up factor n. 5 is unchanged. The new execution time is 13 seconds. Did I have to even run it? Did I have to build it? Did I have to go to the lab? No. You're in a Skype conference call, okay? And there's 5 other bidders on there, and the customer wants to go from 18 seconds to 13 seconds. and you know, because you're an expert and you sold these things before, that you can go from a 3,600 RPM disc to 7,200 RPM disc, or you can do this or that, and it has a certain cost, and you can estimate this and cut the time in half. Doesn't mean going 36 to 72 is going to be half the time, but if you can get some estimate of these, you can get the new time real quick. Other guys are going to go off to the lab and measure this. Amdahl's law. Amdahl's law, this is a time formulation, and now we're going to make it an equation, which is really cool. But let's start with this 1-minute video. So what's going on here? This guy has a job to do. He has to get from point A to point B, and the time is broken into different components. He has to walk to the start line, and now he's made an improvement. He got a bicycle. So he gets there quicker, but the time to get to the bicycle didn't change. So he has to get there even faster. So what does he do now? Gets a car. This is speeding up one part of the system, but leaving some part unimproved. He wants to get there even faster, so he gets a plane. And that's the whole video. I think he says some intelligent things here. So this is a little just example, which is actually showing Amdahl's law, that says that we have some tasks to do, which is this total time depicted here as a pie chart. This is a fixed amount of time no matter what improvements used once he gets to the start line. Very interesting. If I make just this part faster, we can calculate, we just did in the previous slide, that if this is part sped up by a certain factor, the total time is going to be this, which is unchanged, plus this divided by the speed up factor. Something very interesting, which leads us to Amdahl's law. Suppose I have something that's a plane that's so fast, I get a rocket or I get to teleportation, that once I get to the start line, it takes negligible time, 0 time, to get to the destination. What's the maximum speed up possible if I don't improve the time to get to the start line? Turns out to be 1 over this time. We're going to solve that. That's Amdahl's law. So Amdahl's law says there's some component that doesn't change, and we're changing some other things. When we use multiple cores, in terms of our abstraction, what components are we improving? We have multiple cores. We add CPU cores. We're improving the CPU time. We don't touch memory. We don't touch I/O. We don't. So if we're adding 4 cores, I can take this time and divide by 4 if this is a CPU time, but the time for memory is left alone. Amdahl's law is going to give us a bound on that. So Amdahl's law tells us how much can multiple cores help us to speed up a program in an ideal limit and in practice. A nice way to formulate this problem and to understand it is to look at speed up in terms of the old execution time divided by the new execution time. As a matter of fact, I put a red box around it. That's the definition that you want to keep in mind for speed up. It's the execution time on the old system, which means before you improved it, divided by the execution time on the new system. So if that number comes out to be, let's say, 1.5, that means the speed up factor of 1.5 means 50% faster with the new system versus the old. We can also divide through by old execution time and get the fraction enhanced in this form. So we see here there's something called fraction enhanced, was the proportion of code. Go back to our runner that we had in the previous lecture, and there was a little video, right, animation. And we said there was some time to get to the start line, which according to the pie chart was maybe 1/6 of the time. That would be the fraction that's not enhanced. And 5/6 of the time was sped up by what? He got a bicycle, he got an airplane, all right, and it went faster. So that was the fraction that was enhanced, was 5/6 of the total time to complete that task. What was the speed up? Well, when he had the bicycle, maybe it was twice as fast as running, and then when he had the car, it was 10 times faster. So speed up factor was 10. So these are the terms, and I want you to be able to relate those to the animation. So let's go back to the computer example that we had. We had 3 components of execution time. in this abstraction, right? It's abstraction. CPU time was 3 seconds, memory was 10, hard disk was 5 seconds, and the speed up factor was 2. So we calculated last time that the new execution time would be 13 seconds. Another way to calculate it, you can use Amdahl's law in this formulation using the speed up factor. So we said that memory was going to go twice as fast under this improved design. So we can say that the speed up, right, calculated here, we had the execution time 18 originally and 13, right? 18, 3 plus 10, 13 plus 5, 18. The new time would be 3 plus 5 is 8, plus half of 10 is 5, or 13. Another way to calculate the speed up, which is time old divided by time new, is to simply take this equation and say it's 1 minus the fraction enhanced. Well, what was the fraction enhanced in this example? We're only improving the memory system. So, what's the fraction? Well, the total time was 18, and the memory was 10 of it. So that's 10 18ths, so 1 minus 10 18ths is 8 18ths. And here's the fraction enhanced, 10 18ths. What's the speed up factor? Well, that's given in the problem. Speed up factor is 2. We end up getting the same speed up factor if you calculate the ratio of times or you use the fraction enhanced. Actually, they're connected, and we can see that from the animation of last time. So what does this number mean? This number means that we're improving some part of the system, memory, by a factor of 2. Overall, the system is 1.38 times faster, or 40% faster. So you can go if you want. This is outside of class activity. I don't think we need to do it together, but you can click on here, and there's actually a nice interactive. People use Wolfram Alpha. Yeah, it's from the MathCAD people, but they make it on the web and free, and it's actually pretty nice. You can buy an upgrade, but you don't have to. But you can go there and you can change some of these fractions and see what this equation looks like. I provide you a few graphs. So let's look at this equation and what does it mean, and I want you to understand it, and then you don't have to memorize it. You shouldn't need an equation sheet for any of these, actually. So we have a formulation here, and what we're going to do is take the ratio as we defined it. Speed up was defined to be the time, if we're going to use multiple cores, this is the old time without enhancement, and this is when we're executing on n parallel processors, which means n cores. That's the new time. The new time is when we have multi-core version versus the unicore version. So that running time, let's just call it T, is the running time. Is some quantity of seconds. I don't know how many seconds, but we'll just say T. We'll just give it a variable T. What I'm going to do is decompose T into two components. 1 minus f times t plus t times f. What's f? F is a fraction. Was a fraction enhanced? And what is f? F is a unit list ratio between 0 and 1. So f is a fraction enhanced. So if 100% of the execution is sped up by this enhancement, f would be 1.0. If none is enhanced, it's a 0. So this numerator adds to what? Numerator adds to? Nope. It adds a t. All right. So don't be scared of this. You look at this, it's like, there's no way I can, people like the mental block. No. That's t. That's just breaking t into two parts. Yeah. Right? Because this is, pick a value for f, 0.4. So this is 0.4 t plus 0.6 t is t. We're good, right? And then what? What's in the denominator is the time on n parallel processors. Well, what happens when we run on n parallel processors? You have some fraction you don't enhance. The time's unchanged. See the numerator and denominator is the same? What about the part of the program that you did speed up? How much faster does it go? What factor? 1 over n times faster, which meant the time was divided by n. You're exactly right. Is there any like super hard thing about that? No, but actually this is a very powerful equation that you can use, and we're going to show this. When we have some measurements, just a few measurements, I can tell you how much faster it can go on 5 cores, 6 cores. They have 6-core Xeon, but 4-core, 8-core. Give me any value, I'll tell you, or even 1,000 processors. What's the speed up? I can bound it. Okay, and we're going to find out why. This formulation just simply divides through. You can try it as a challenge algebraically. I did it on the side of a piece of paper. You can divide through here and get this form. Okay. Get rid of the t's. Right here. 1 minus f. Okay. All right. Here's an example. Over 40%. Ideally, what is the maximum speed up? So here's our first application of this. We like to take limits because limits help us envision and understand the behavior of a system or an equation. What is the maximum speed up regardless of how many cores are used? So here is our speed up equation. I'm going to use the letter S. 1 over 1 minus f, f over n. N is, what are these quantities in this declarative statement? We're speeding up the execution by using multiple cores. So, all right, make it easy. What's F? Yeah. So we can make a little symbol table over here. F is 0.4. Sounds good. And what else do we need in this equation? There's only 2 variables. And what's N? Infinity. Exactly right. Okay. We use this symbol for infinity just for convenience, but we can talk about that. Anyway, so let n equal infinity. So what happens to this equation? You can take the limit. You thought you'd never use that, right, from calculus, right? N goes to infinity of this of s. What does that equal? Good. This term, this starts to, n gets larger and larger and larger. This term gets smaller and smaller, eventually approaches 0, becomes diminishingly small, and what are you left with? So, 40% of your application can be sped up using multiple cores. No matter how many cores. I give you 4 cores, 8 cores, 16 cores, 1,000,000 cores. What's the maximum speed up that you can speed up that application? What's that number? 0.6. It's not a big number. 1 2/3. Let me state this another way. We saw a top 500 Tehani supercomputer, 3 million cores. If the application that they're running is 40% parallelizable, which means that 60% of the code is not, which is what? Maybe initialization, data access to the disk drive, latency, delays, things that have to be done in steps. No matter how many cores you throw at the problem, you can't make it more than this % faster. That's really important. Now we go back to the Apple iPhone, had dual core, and somebody else had quad core, and you want to fight about it? Well, we always measure a benchmark, okay, and look at it. But unless we have a lot of things to do in parallel, adding more cores may not make it that much more fast and speed up our application. So in this particular case, F here, we're having unlimited cores, unlimited 1.67 fold speed up. Using additional cores cannot make it faster. Okay. Someone want to put some real numbers in here? Suppose I gave you it's interesting, right? It's an interesting equation. We're going to see the graph of it here. Change different values of speed up versus n. And this is kind of the curve here. But if you put some values in, right, let's fix this. F is 0.4. It's coming up. So in this particular example, S 1 over 0.6 plus 0.4. Suppose you have n equals 8 cores. All right. What's the speed up? Somebody have a calculator? We can do it on a computer. What's 4.4 divided by 8?
0.65.
Okay, so I already put this in. Somebody, this is going to be 0.5, right? 5 times 8 is 40. All right, so this is 0.5. Okay, you're right, 0.65. And then we do 1 over that, right? What's about 1 over a half? Still less than 2, right? It's not quite 2, right? Because this is this is over 0.65. So going from 8 cores to 10, a million, a billion cores doesn't speed it up much more. You've already maxed out. It's diminishing returns. It's diminishing returns. So one thing I want you to walk away from is this nice understanding, this nice relationship. The speed up is bounded. I'll say it in English here. Speed up is bounded by 1 over 1 minus f, no matter how many cores you throw at the problem. If you want to get a high speed up, you need a high fraction. You need a very close to 1 fraction parallelizable code. Otherwise, the cores are just sitting there. They have nothing to do. Okay, we'll try some more examples. So here's a program. We're going to put this to work. 10 seconds. On a dual core Xenon, they can go up to 6 cores. 2 gigahertz clock rate under ideal conditions. We say ideal conditions because we can apply this without worrying about overhead and other unideal execution time. So we have a lot of components execution time. Here we're just talking about processor. Either it's parallelizable, it's F, or it's not, 1 minus F. Program has 30% sequential code. Remainder is infinitely parallelizable. What is the minimum time to execute this program? On an 8-core Xenon processor, round your answer to the nearest second. So first thing we want to think of when we see this problem, we can apply Amdahl's law. We have a fraction that's parallelizable. We have a running time. We can substitute this. We have one equation with 2 unknowns, and both values are given. We can solve. But the interesting thing about this problem is they're giving you the running time of 10 seconds. Is it on a uniprocessor? No, that's on a dual core. So we have to back out, because what we have here in Amdahl's law was the time on a single processor. What was given in this problem? Dual core. So we have to go from dual core to single core to figure out what the execution time was on 1 core, and then from 1 core we can go to 8 cores. Why? Because that Amdahl's law is based on the uniprocessor case. So the minimum time to execute this program, we can calculate as follows. First, we're going to observe the parallel portion is 0.7 because the sequential portion was 30%. It's either parallel or sequential because this is the ideal case. First, compute the dual core speed up when we have a 0.7 fraction. We use Amdahl's law and you find out it's 1.54. That's very interesting. So when you have a 70% speed up, I put 2 cores on this problem. 70% fractional, parallelizable. I put 2 cores on this problem. It went almost 1.5 times faster, a little bit over 1.5 times faster. So if it took 10 seconds on dual core, what was the time on the single core? The speed up was 1.54, 15.4 seconds. Everybody okay to hear? Then what? We know it's 15.4 seconds on 1 core. I've given you the fraction is 30%. That's enhanced. I've given you 8 cores. What do you think? Amdahl's law. Amdahl's law, 1 over 1 minus f plus f over n. All right. What's F? We know N. Speed up is 2.58. Does that mean 2.58 seconds? Yes or no? Sorry. 2.58 seconds?
No.
No. It means it's 2.58 times faster. How many seconds was it? 15.4? So, divide 5.97. So we always look at the numbers and see if they're at least intuitively consistent. On 2 cores, it took 10 seconds. So based on the fraction, we computed that it took 15 seconds on 1 core. On 8 cores, it took 6 seconds. Okay. We wouldn't expect it to take more than on 2 cores. Maybe we made an error calculation or typing or something, calculate. So the numbers are reasonable, but we see this type of behavior when we increase the number of cores, it doesn't scale linearly. Because we're only improving some fraction of the total time. Go back to the runner. Yeah, he made 5/6 of his time to get from point A to point B faster, but he still had to get to the start line that was, according to that pie chart, 1/6 of the time. That 1/6 is there no matter what. What's the maximum speed up if he gets, a rocket, or what? Teleportation. He wants to get from point A to point B, and it takes 1/6 of the time to get to the start line, to get to the teleportation machine, right? How much faster can he go versus walking? I heard a number.
6 or 5, 6.
6. 1 over 1/6. 6 times faster. The way to think about this is a way to think about this. If you make this term diminishingly small, what are you left with? You're left with the part you didn't change. Maybe we look at it in terms of time, maybe easier to see. Yeah. Let's just look at the denominator of this equation. Let's look at this formulation. If I make n very, very, very large, teleportation, so that it's like the time that is improved goes to 0, the proportion of time, the component of time. Just looking at the denominator, what time are you left with? The time you didn't change. So if that's 1/6 of the time, your maximum speed up is 6. It's 1 over 1 minus f. Okay. If you want to think of Amdahl's law in a very practical way, suppose you're moving. You're moving from one place to another, and you get your friends to help you, right? And because it's a long process and they're heavy things, and you have people help you, right? You have one, you do it by yourself, it takes, it takes a day. You have your friend come and it speeds it up, but you still have to drive the truck from where you started to where you're going. No matter how many friends you come help you, you're stuck with that time. So suppose you had infinite friends, they're infinitely efficient, which my friends aren't, right? You buy pizza and they're, you start talking and then, but if they're infinitely efficient, you can make everything but the truck driving time go to 0. What are you left with? The part you didn't enhance. What does Amdahl's law say? Exactly that. When is that helpful? Well, if you give me the number of cores, you give me the time on one processor or one core, I can tell you it can't go faster than the maximum speed up if you had infinite cores, which actually may not be a very large number. This is very interesting, okay? Very practical. Let's look at some graphs for Amdahl's law. Typical number of cores, maybe 1, 2, 4, 8. So we have some graphs here. You have a linear speed up. Linear speed up means I increase the number of cores, I get a speed up factor equal to n. So I have n cores, it goes n times faster. What was F? 100%, exactly. 1.0. F at 1.0 in practice, well, that's the perfect world, right? But just like moving, right, is you have to still drive the truck, and no matter how many friends you have, no matter how many cores you throw at the problem, you still have some time that you don't improve. In a computer system, what's some part of the time we're running a program, we want to execute? What's some part of the time we typically cannot improve by using multiple cores? Give me some examples. Yeah, good. Network time is out of our hands, right? If we're improving the processor, throwing more cores at it, we didn't change the latency. Exactly. How about some other ones? That's a very good one that we see, especially in network environment. Yeah. Oh. Data transfer time, another type of latency. That does not change by having more cores. How about initialization in your program? You know, I equals 0, all these setting these variables. Doesn't change. How much time is that? Well, depends how much initialization you do. What about error control? That's usually sequential too, right? No matter how many cores you have, something happens, you have to do one at a time, figure out what to do, right? So, will more processors help much? And we see that this thing levels off, and this is like diminishing returns, right? Once you have enough friends to your house, then, well, that's as fast as you can move. What about very limited F? You see if F is very limited, like this is a serial percent. So here if we have a very high parallel, which means the serial is small, you can get a high speed up. But once here you have 1,000 cores, yeah? Once you get above like 0.25% sequential, which means 99.75 can be made parallel, which sounds pretty good. Even with 1,000 cores, where do you end up? 300 times faster. All right. Let's try another example. We have a web application. It's running with the following characteristics. 40% of the time is spent in computation. And as you suggested, 60% of the time is spent waiting I/O. It may be realistic. A new CPU will make the processor 10 times faster but cost $500. Your manager will authorize the purchase only if it speeds up the web application by a factor of 2 or more. Very realistic. Should you buy the new chip or not? Without buying the chip and measuring it, can you think, is it even possible for this to work? You think Amdahl's law. Here we have the speed up we're going to calculate, right? What's the speed up that the manager seeks? 2. So we're going to compose this as the fraction that's unenhanced, right? Because 60% of the time was I/O. What are we improving? We're improving the processor time by having a faster processor. That's 40%. What's the speed up factor? 10. Yes or no? Do you want to tell the manager to do it or no?
No.
No. Okay. Can you use Amdahl's law in a meeting? Can you use Amdahl's law on a Skype phone call? Can you do it on a piece of paper? Yes. Can you do it without measuring it, without compiling, yes. There's no way to achieve what this guy wants. Just tell him right away. Here's another example. We have 3 components of execution time. 3 seconds, 10 seconds, 5 seconds. Again, it's the same problem we had before. Now, what's better? To improve the processor be 2 times faster, or, it's exclusive or, cookies or ice cream, right? Not both. Or make the memory 2 times faster. Suppose they're equal cost. Amdahl's law to the rescue. We can evaluate these 2 cases. This is the case where we have, right, the speed up with the faster processor was 1.1 basically. Speed up with faster memory was 1.4. If they're equal costs, we're going to choose a memory option. You're going to say, okay, this seems like a number, I can't imagine it. Always go to the human units. We can convert to units of time, right? Seconds is something humans can comprehend. So what was execution time in seconds of these 2 choices? Faster memory gets the job done faster than faster processor. You're going to say, well, give me different values to be different. Absolutely. That's why we need Amdahl's law. So Amdahl's law reminds us as designers these relative ratios of memory and processor. We call it a bottleneck, right? And here we see a balanced system and an unbalanced system, or a constricted system, what we call I/O bound and CPU bound. You can hear these words in a job interview. Yeah, we have an I/O. Our applications are typically I/O bound. They look like this, okay? It means that we have enough processing capability, but the size of the pipe to get data in and out is not big enough. Okay. If your system's unbalanced, your data bus is too slow, doesn't matter how fast your processor is, because you're diminishing returns. You've already maxed it out. We can see this here, right? I like the water flow model. Okay, I know electricity and water don't mix, which is true, but the analogies are very, that's where they came from actually, because 1700, Volta and these guys are just picturing, something flowing from point A and B, and they don't know how it works, so they just imagine water, and that's the current, and all these terms that we have. So, imagine tasks flowing through this pipe. If it's CPU bound, we get to the CPU, it's not big enough capacity. So here's another example. This is a good one. So we have a MIPS brand processor. Floating point is 40%, integer 30%, data transfer 30%. These are different instruction classes. They have different number of clock cycles. Okay, which one do we want to speed up? We already saw some examples in the previous module of doing this. In part A, this method is proposed to make floating point 8 times faster. What's the speed up? And then part B, we're going to add an additional enhancement. We want to increase integer by 2-fold. What's the overall speed up? So part A solution is direct application of Amdahl's law. You should be able to find, if your customer gives you a declarative statement, you should be able to take that and populate this in something that makes sense to you. Even if you forget what these things are, if you understand the basics of Amdahl's law, which is saying time old divided by time new, and you can write time old as a fraction of t, just always remember, fraction of t that's enhanced or unenhanced, you can derive it in about 10 seconds. So here we're going to substitute in, you get 1.538 for the first improvement. Something cool, if you have multiple improvements, you can use this, convert this back to a time, and then apply an improvement on that like we did in the 2-core and 8-core, or you can use this formulation. We have some fraction that's unenhanced, and we have 2 enhancements. So now we're going to think about 3 fractions. Okay? So there's a fraction that's not enhanced, fraction enhanced with improvement 1, fraction enhanced with improvement 2. What's the speed up factor for each? Well, that's given in the problem. How much faster will it go? Whatever the speed up factor is for that enhancement. Can I get this number quick? Yeah. 1 over 0.3 is unenhanced. 0.4 is floating point. 0.3 was integer, going twice as fast. Give you nice numbers. I try to give you nice numbers most of the time, and here's it comes out to be a half, and then that's 2. How much faster? Twice as fast. I'll let you guys ask some questions. So to me, this is really great, right? I mean, this is a real situation, and it fits on one slide. Okay, yeah, the real world might be a little bit more complicated, but here we're giving you 30% this trade-off, and somebody tells you so many clocks for this, so many clocks for that, or percent of the total time. Is it worth it to do this or that? It's nice.
In reality, is it always 1, 2, 4, or 8 cores just by the...
Yeah, we're going to have a module. Mr. Gray is on a nice track there. Powers of 2, and the reason why is because they build a device and they make a copy of it. And they make a copy of the copy. So you got 2 and you get 4. You make a copy of the copy of the copy, you got 8. Why? It's just, once you debug it, you just make a copy of it usually. And some of the way we're going to see actually that we don't get a chance in this class, but if you take another class, a computer architecture class, you see the way you route data is with a bit string that's saying the address you want to go to, and if those are a multiple of 2, you don't need extra wasted bits, which makes the routing really easy. Other questions on this? So there's problems in the study set. You can take a look at these. We try some more examples. Here's one processor, spends 60% of its time integer. Your project team's considering improving the arithmetic unit. So now I'm taking this to the next level. I saw this in a real case working with a company. about 5 or 6 years ago, there's always a cost to making an improvement. We saw an example before we have a limited budget. Remember module 2? Yeah. And you had to say processor and the memory and the Toshiba, right? We had to make some under $20, right? Well, here, this is very cool, all right? This is a real case. So what's the minimum, without building the chip, what's the minimum value of N to improve the processor's performance? Okay, let's read the specification again. So here, 60% of the time is integer, 20% branch, 20% data transfer. Your project teams consider improving the arithmetic unit. So that's what? Arithmetic unit. Integer, okay? It's not branch, which is control. Data transfer is load and store. It's got to be integer. To execute n times faster. However, this will decrease the area available on the chip. Data bus is going slower, twice as slow. There's always some trade-off. Right? If we're going to make some part of it faster, we have a limited area. It's called real estate. You want to have a nice garden in your yard, then you can't have a pool. You want to put a pool, then you can't have an orange tree. Same thing here. We want to speed up this by a factor of 2. You might end up slowing down something else. You're going to say, no, I want to do both. Well, you can, but then the chip costs more. They're giving you a limited area budget. It's the real world. So, without building or simulating a chip, what's the minimum value of speed up you need, okay, a factor of n, right, in the processor's performance to make this worth it? So we're going to solve for speed up. We're going to substitute in. Where do we get this 0.6? This was an arithmetic, right? It's sped up by a factor of n. What's n? It's the unknown. Well, I have one equation and one unknown, and then speed up is known or not known. All right, we don't know. So how do we solve this? Well, this is fraction enhanced. This is the speed up of the enhancement, unchanged, and this is a fraction slowed down. So how do we specify we're slowing it down? Instead of dividing by n, we multiply by 2. This proportion takes longer. Right?
Can't be.
So then, yeah, go. You got it. You got it. Go.
It can't be more than twice because the fraction's already points.
That's true, but when does it become worth it? Definition of speed up is time old divided by time new. So if my speed up, pick a boundary condition. If my speed up is greater than this or less than this, or 1. If my speed up is greater than 1, it was worth it. I made it faster. If I'm not speeding it up, don't do it. It's that simple. That's a slow down factor. We just answered that. So this is the speed up of the entire processor is this equation. If it's greater than 1, it meant that this was worth it. So we're going to set this greater than 1, and we're going to solve for n. It's an inequality. Should you be able to reason through this? Yeah. Is it something kind of interesting? Yeah. To me, it's very interesting because you can get this in a meeting and solve it without building the chip. Turns out if you put these numbers in and you solve this, everybody can solve this inequality. Okay. You end up that n has to be 1.5 or more. What does that mean? That if you're going to make the data bus twice as slow, this arithmetic has to be 1.5 times faster. What percent? 50% faster, or don't do it. Why? Why not do it? Because you'll be slower on the whole. Until you get to 50% speed enough to, well, why is this 50 when this thing is twice as slow? Because this was 60%. This was 20, but then we had another 20%. So, unchanged. So it's kind of like the unchanged has weight of 1, and the slowdown has weight of 2, and the speed up has weight of 2, and then you get the 2 to 1 ratio. Yeah, give me different numbers, you're going to get different value, but that's what equations are for. What do you guys think of this? Kind of cool. Arithmetic unit has to be at least 50% faster, or don't do it. Last example, real world, totally real world. Okay. You have a company and you're doing consulting, or you want to bid on something that's on what Amazon has the Mechanical Turk thing. You can build little jobs, or you can go and get these tasks, right? Avoid the fallacy of focusing on one aspect, okay? So here's an example. Someone says, you know, they want to hire you. They want somebody to improve their system, and here they have this task. It's 80 milliseconds of 100 is for an encryption task, okay? This is a FIPS, is a type of encryption. They're going to pay you $50,000 plus expenses if you can complete it in 20 milliseconds, should you bid the job. Amdahl's law can help us figure it out. Here we're going to apply the concept of improvement factor. Time improved is the time affected divided by the improvement factor plus the unaffected. We just interchange the two. Commutative. Addition's commutative. So we're solving for n just like we did last time, but now we want it to be 20 milliseconds, and the 80 has to get reduced so that 80 divided by n plus 20 is less than or equal to 20. Is there any value of n that makes it happen? No. Right. Doesn't matter how good a designer you are. Doesn't matter how good your chip is. Doesn't matter how fast it is. Doesn't matter if you overclock it. Doesn't matter. You're never going to make this customer happy. These are like bad, you know. Sometimes you get in these things. Of course, they don't give you the money till the end, right? So you end up working on this for 2 months, and then at the end, you're just like, I can't do it. And then you lost a lot of time. But here you can figure out right away, you know what, how, even if this is possible, is like, how possible is it? You can use Amdahl's law and say, you know what, that's a really hard job. Maybe I want to scroll down the page and pick an easy one. Low-hanging fruit, right? Again, we see this, if you make n very large, right, this term gets close to 0, yeah? And you still can't meet the customer's objective. But then we're getting back to this divide by 0 business, right? I'll let you guys ask some questions on this one, and then we're done. Okay, I'll let you ask some questions. Amdahl's law. How about the infinity and divide by, so I said some, so just an aside, because we got all our work done, now we can have fun. You know, in math class, they tell you this, right? It's okay. It's not wrong, but it's good if we can understand. They'll tell you that infinity, you know, is defined to be this symbol here. Question. It matters in this a little bit. Yes or no? And why? So in math class, they tell you yes, right? What does it mean? What is this? Yeah. You can pick any number, right? Divide by 0 is what? Yeah. I like this word, actually. I think it is undefined. Sometimes they tell you it's infinity. We write that symbol, but infinity is like a number that's so large you can't quantify it, right? It's unbounded. But let's think of it this way. What does this mean, right? If you take, let's see, 6 divided by 2 is 3. That's an equation. We've written it since 4th grade or 3rd. What does that mean? If you have, yeah, go ahead. What's that?
3 times is 2 going.
Exactly. So if you have 3 2s, you get 6. If you have infinite zeros, do you get x? No. I don't think it's true, actually. It doesn't. It's undefined. That's why we use the word undefined. We're going to see in the floating point, which is our module coming up in 2 modules, they have something called not a number. Not a number is what we designate when we don't have an answer. We do a calculation like divide by 0. The result is not a number. It's undefined. It's one type of not a number. You can overflow, be too large, and end up with a number you cannot represent. But the key thing to keep in mind is when we divide by something that's very large or very small, we can use this symbol, but just remember that the symbol is not necessary. It's in the limit. In the limit is true. In the limit is true. But is it ever exactly equal? No. No matter how many zeros you give me, I'm never going to get a finite amount. Mr. Gray.
Why does your program crash? Like, what is the computer's?
So the program can crash, or you can what's called a vector to some handling routine, or we use interrupt, which we'll talk about maybe. Why? Because it's a very actually good example. We have here a robotics club, and we had the DARPA challenge. Anybody know the DARPA autonomous vehicle challenge? Before Google had their car. Okay, so around the turn of the century, a long time ago, before Google had self-driving car, DARPA had a contest, and some of the best universities competed. UCF did really, really well. We have a technician, his name's Don Harper. He's been in our department a long time. He keeps all the computers running, actually. And he just loves to build stuff and work on stuff. And he actually volunteered. He just donated his car for this project. They had cameras mounted on the top of it. They drilled like holes in this roof, and just because he likes to, do this stuff. The interesting thing was they got to the finals, and they went out to 29 Palms. Anybody been to Southern California? Yeah. What's out there? How about, yeah, go ahead.
It's a Marine base.
Yeah, Marine base, and it's like desert. There's nothing there, right? Palm Springs. Anybody been to Palm Springs?
California.
You guys gotta get out more. So. Yeah, this desert. There's nothing there. Okay, they make it sound nice, right? But because they plant some palms and they water it, it's like in the winter it's great. In the winter, yeah, it's awesome. But in the summer it's like 115 degrees, whatever. So anyway, they get out to the desert and they have this like fake town, and they practice military training and stuff, and then they're supposed to drive through this town. So UCF's car gets out there, and we're doing really well, and we're down to CMU, MIT, top guys, and UCF's right there, and then all of a sudden the car just stops, and it got a division by 0, not a number. And what happens is, suppose you get a calculation and the answer is not a number. I'm sorry that you can't see it, but once you get a calculation that's not a number, what's 3 plus not a number? Not a number. What's 5 times not a number? Not a number. So once the calculation failed, and it wasn't UCF's fault because they used a public domain library and someone didn't check for division by 0 and stop it, once they got not a number, all the calculations were bad. So when we divide by 0, we have a way to handle that. Usually we have some software routine to handle that. So it depends, what does it mean, right? If you're dividing by 0, it means that maybe whatever they were doing in this case, they got to an intersection and they had to say, am I going left or right, or how many degrees? I don't know the details of the calculation. You could talk to Don Harper, he'll probably remember. And maybe the angle that they had to turn was very narrow and it came to 0, and then the algorithm doesn't know what to do. So that's what happens. Yeah. Other question in this one? What do you guys think? Okay. Amdahl's law. So here's summary for this module. Benchmarking, we had geometric mean. Geometric mean, the ratio of the means and the means of the ratios is retained, which is great because we can use a reference machine. If I get my value to the reference machine, you get your value to the reference machine. The ratio of those two values is our relative speed up. I can make a table. Every computer to the reference, I compare mine to another computer, I know the relative speed. Amdahl's law, I showed you how to derive it.